If you stand very close to an antenna, the electromagnetic fields behave one way. Move farther away, and the behavior changes completely. Surprisingly, an antenna does not create a single electromagnetic environment. Instead, it creates different regions of space, each with unique field characteristics that are critical for RF engineers to understand. Throughout this playlist, we have discussed electromagnetic waves as if they simply radiate outward from an antenna and travel through space. This description is useful, but it hides an important detail. The electromagnetic fields surrounding an antenna do not behave the same way everywhere. Engineers quickly discover that measurements taken close to an antenna often look very different from measurements taken farther away. Field strength, energy distribution, and wave behavior can change dramatically depending on the observation distance. This creates an important question. At what point does an electromagnetic field become a true propagating wave? To answer this, RF engineers divide the space around an antenna into regions known as the near field and the far field. The near field is the region close to an antenna, where electric and magnetic fields exhibit complex interactions and do not yet behave like fully developed radiating waves. In this region, energy is continuously exchanged between electric and magnetic fields. Some energy radiates away, while some remains temporarily stored around the antenna structure. The field distribution depends strongly on antenna geometry and observation distance. The far field is the region sufficiently far from the antenna where electromagnetic waves behave as stable radiating waves. In this region, the electric field and magnetic field are perpendicular, maintain a fixed relationship, and propagate energy outward in a predictable manner. Most antenna performance parameters are defined in the far field. Intuitively, imagine throwing a stone into a pond. Near the point of impact, the water motion is chaotic and complicated. Farther away, clear circular waves emerge and travel outward smoothly. The antenna environment behaves in a similar way. Physically, consider a dipole antenna transmitting an RF signal. Very close to the antenna, electric and magnetic fields vary significantly with position and interact strongly with nearby objects. As distance increases, these complex interactions diminish, and the fields gradually form a stable electromagnetic wave traveling through space. Mathematically, near-field components decrease much more rapidly with distance than radiating far-field components. Eventually, the radiating fields dominate, creating the familiar wave behavior described by electromagnetic wave theory. This transition defines the boundary between the near-field and far-field regions. Understanding near-field and far-field behavior is essential in antenna engineering. Antenna radiation patterns, gain measurements, directivity calculations, and communication range analyses are typically performed in the far-field region because this is where wave behavior becomes predictable. Near-field behavior is equally important in applications such as RFID systems, wireless charging, NFC communication, inductive coupling, and electromagnetic compatibility testing. These technologies intentionally utilize near-field interactions rather than conventional radiating waves. At the system level, distinguishing between near-field and far-field regions helps engineers design antennas, evaluate wireless links, perform measurements correctly, and predict electromagnetic interactions in practical environments. The distinction between near-field and far-field reveals that electromagnetic radiation is not simply a wave that appears instantly at the antenna. Instead, there is a transition region where energy storage and radiation coexist before stable wave propagation emerges. A common misconception is that all antenna measurements are valid at any distance. In reality, measurements taken too close to an antenna may not accurately represent its true radiation characteristics because near-field effects dominate the results. Understanding near-field and far-field behavior completes many of the fundamental concepts needed to analyze electromagnetic waves. In the next lesson, we will conclude this playlist with EM Fundamentals Summary, where we will connect all the major concepts learned throughout our journey into electromagnetism. In this lesson, we learned that the electromagnetic environment around an antenna is divided into near-field and far-field regions, each with distinct characteristics. We also saw how near fields involve energy storage and complex field interactions, while far fields contain stable radiating electromagnetic waves used for communication. In the next lesson, we will conclude this playlist with an EM fundamentals summary and connect all the key concepts that form the foundation of RF engineering. If you found this useful, like the video, subscribe, and follow for the next lesson.